Hey, welcome back. So let's look at what the size of the equilibrium constant is telling us. So very roughly speaking, the equilibrium constant has got something to do with the concentration of products over the concentration of reactants. So my little squiggly line here is essentially just saying it's not equal to, but it's related to. And again, I'm missing the stoichiometric coefficients, but hopefully you can see that it's sort of roughly products over reactants. So given that, then if the equilibrium constant is much bigger than 1, that's really telling us that the concentration of products is much bigger than the concentration of reactants. Whereas if the equilibrium constant is much smaller than 1, then the concentration of reactants is much bigger than the concentration of products, right? So if it's much smaller than 1, the bottom is big and the top is small. And if the equilibrium constant is approximately 1, then it's telling us that the concentration of reactants is approximately equal to the concentration of products. So very, very crude, but that's roughly what we can tell from an equilibrium constant. So if it's on the order of 1,000,000 or 1,000,000,000, essentially we've got all products at equilibrium. So we can think of those as normal reactions probably. If the equilibrium constant is very small, like 10 to the minus 6, essentially there's no reaction. You've got all reactants at equilibrium, very few products. And if your equilibrium constant is about 1, that's telling you that at equilibrium there's going to be similar amounts of reactants and products. Now, you might ask yourself, how small can an equilibrium constant go? And the answer is it can't get below 0. It can't be negative ever, because it's impossible to have a negative concentration of products or reactants. So let's look at a couple of equilibrium reactions and look at their equilibrium constants and see what that's telling us. So hydrogen plus bromine making hydrogen bromide, so excuse my sloppy equilibrium symbol there, has an equilibrium constant Kc of 1.9 times 10 to the 19 at 25 degrees C. So these may be constants, but they're only constants for a particular temperature. Because K is so insanely large, then essentially at equilibrium, it's going to be mainly products. However, if we take another chemical reaction, so that between nitrogen and oxygen, maybe these are the components in the air to make nitric oxide, this equilibrium constant is exceptionally small. So it's 4.1 times 10 to the minus 31 at 25 degrees Celsius. So that's telling us that we're going to have mainly reactants at equilibrium, which is probably a good thing because nitrogen and oxygen in the air, right? It would be sort of embarrassing if they reacted and made nitric oxide, which is poisonous for us to breathe. So again, I've said reactants and products. I shouldn't really use reactants and products in an equilibrium because the reaction can go in both direction. But there's mainly HBr in this one up here, and there's mainly N2 and O2 in this equilibrium down below.